Symmetric functions. What are symmetric functions? And how can we use the symmetric properties of a function to evaluate integrals involving such a function? All right, so first of all, let's look at symmetric functions. What are symmetric functions? Symmetric functions. So these are odd and even functions. What makes the function odd? What makes the function even? Okay. A function f is said to be odd if f of negative x is equal to negative f of x. All right, so a function is said to be even if f of negative x is equal to f of x. So diagrammatically, what does this mean? Let's try to sketch an odd function. So if we have a function, say this is our y-axis and this is our x-axis, let's get a green function. Or let's get a black function. So this is the graph of the function. If it's like this, and then this is x and this is negative x, right? This is our x-axis and that's our y-axis, right? So we can see that for this function, make it a little larger. This function, it crosses the x-axis and the y-axis at the origin. And when we have the value of f at x, at any x, is the same thing as negative times the value at negative x. So this function is it's odd. This is an odd function. And this function is symmetric about the origin. Now let's draw another function. Let's try to draw an even function. Say we have this function, like this. You know what, before I continue, I want to change this. Instead of calling this x and negative x, I want to call it a and negative a, because we've used x for the name of the horizontal axis. All right, so if we have a function that behaves like this, maybe like that, this is really symmetric. All right, and this is a and this is negative a, and both a and negative a have the same values. Such a function is known as an even function. So the definition now is beginning to make sense, as we can see. So let's see, put this here. This is our x-axis, and that's our y-axis. So this function is symmetric, or it's an even function, and its graph its graph is symmetric about the y-axis in this case. Okay, why are we doing all this? Because we would like to make use of these properties to compute integrals. So if you look at this already, if you have a function that is symmetric about the origin, an odd function, and if you try to compute the integral from negative a to a, automatically you see that this integral is going to be 0 because this is a positive area and this is a negative area. And the integral from negative a to a is just going to be, so if this area is a, then this area would definitely be negative a. So if you add both of them up, you get 0. However, if you are dealing with the area under a curve, which is the integral, the definite integral, for an even function from a to a, if this area is a, this area is definitely going to be a. So if you can compute the integral from 0 to a, then you can compute the integral from negative a to a easily by just multiplying the integral from 0 to a by 2. All right, before we proceed any further, let's look at some examples of odd functions and even functions. So I'll let you verify this by graphing and sketching. So examples of odd functions. Or examples of an odd function. So the function, these are just a few examples. The function y equals x is an odd function. Why? So if you draw the graph, it's quite easy to see. This is an odd function. All right. How about if you look at y equals x cubed, right? So if you have x cubed, oh no, x cubed is like this, Let's look at another one, classic odd functions. How about y equals sine x? Kind of looks like x cubed, but it's not. Okay, y equals sine x. So in general, if you have a polynomial, or if you just have a power function that has the power, that has an odd power, an odd integral power, that function is definitely an odd function. For instance, y equals x is odd, y equals x cubed, y equals x to the 5th, y equals x to the 7th. All right, so those are all odd functions. And then we have some other classic odd functions like the sine function. Okay, so how about we look at the even functions, examples of an even function. Okay, so x squared, in fact, anything that has the form y equals x to the power of a, and a is a positive even number, then that function is definitely an even function. Right. Okay. But then there's one very easy even function. So where k is a constant. Right? So this is an even function. And then another function, a classic function, the cosine function, is that. Etc. All right. So now let's do some exercise. Let's do an exercise. Let's determine, without graphing, determine if the function is odd, even, even, or neither. Okay? So let's start with the first one. Let's start with f of x is x squared plus 1. You can sketch this and tell if it's an even function or an odd function. But how do we do this without having to sketch? Now, sorry, there's a lot of noise in the background. I'm very sorry. But we can do this just from the definition of an odd and even function. What is the definition? We start with f of negative x. If f of negative x ends up being f of x, then it's even. So f of negative x is negative x squared plus 1, which is just equal to x squared plus 1, which is f of x. So the function is even. Let's try another one. How about f of x is x cubed x to the 5th plus x. So again, we look for f of negative x, which is negative x to the power of 5 plus negative x, which is negative x to the power of 5. If you multiply negative x 5 times, you get negative x to the power of 5, and then you have negative x, which is the same thing as if this is not even. We can see that this is definitely not even because it's not equal to. So let's do this. Let's just say this is not equal to f of x, so not even. But let's see, if we factor out a negative, we'll be left with x to the power of 5 plus x, which is negative f of x. So this function is definitely odd. Okay? Odd, even. Now, let's try another one. How about g of x? G of x is x cubed plus 1. So let's try g of negative x which is negative x to the power of 3 plus 1, which is the same thing as negative x cubed plus 1. All right, so this is definitely not even. At least we can tell that it's not even. So let's try to see if it's odd. If we factor out a negative, we'll be left with negative x cubed minus 1. So this is not odd. Definitely not odd. So let's go back and investigate a little, just say a little bit more. Why is this not even? Because this is not equal to g of x. It's not equal to g of x, so it's not even. And this is definitely not odd because it's not equal to negative g of x, so it's not odd. All right, maybe I should make this blue. Style blue. Okay, so now that we know what an odd and even function is, let us try to do a few things involving integrals. All right, before we do that, let me state a theorem that I already alluded to. This theorem says let A be a positive, let it be a positive real number. And let f be an integrable function. On the interval negative a to a. The first part of the theorem says this. It says that if f is even, then the integral from negative a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. And then b, if f is odd, then the integral from negative a to a of f of x dx is equal to 0. So this is quite easy to see if you go back to our diagram. We talked about this before. So this is 0, have a positive, if you look at the odd function, you have a positive area and then a negative area, right? But then if you look at which, when you add up, they're both equal in magnitude. If you add them up, you get 0. This is equal in magnitude, but they're both positive. If you add a and a up, you get 2a. Okay, so we're not going to prove this theorem because we don't have time for it, and it's just a calculus course. You'll be able to prove this when you take real analysis if you're a math major. So let's do a few examples. All right, so examples. So the first one, let's evaluate the integral from -2 to 2 of x squared minus x dx. What do we know? Now, this is where it's good to know your odd functions and your even functions. So this integral we can write as -2 to 2 of x squared minus, let's split it up, dx minus integral from -2 to 2x dx. Now, what do I know? I know that x squared is even. So, automatically, how about I want to write over here. So, I can automatically say that this is the integral. Wait, hold on 1 second. Why am I doing that? Hold on, I don't want this. I don't want it here. Let me just continue over here. All right. So I can say that this is the 2 times the integral from 0 to 2 of x squared, because x squared is even. And I can actually say that this is 0. Why? My reason is that I need to recall x squared is even and x is odd. All right? And all I'm doing is applying the theorem. If f is even, you multiply 2. The integral from negative a to a is 2 times the integral from 0 to a. If f is odd, the integral from negative a to a is 0. And whenever you have 0 involved in evaluation of an integral, it makes it a little easier in certain cases. So we have 2. We evaluate the antiderivative, x cubed over x cubed over 3 from 0 to 2. This is 2. You plug in 0 and plug in 2. But when you plug in 0, you just get 0. So why not just plug in 2? You get 2 times 8 over 3, which is 16 over 3. All right. Now let's try another one. Let us try let's try the integral from negative pi over 2 to pi over 2 of cosine x minus 5 times x dx. All right, we know that cosine x is an even function, so we can go from negative pi over 2 to pi over 2 of cosine x minus 5 times negative pi over 2 to pi over 2 of sine x to the power of 5 dx. Okay. I want to mention something here. If you have an odd function and you raise it to the power of an odd number, you get an odd function. If you have an odd function and you raise it to the power of an even number, you get an even function. All right? Okay. So all I'm trying to say, to point to, is that this part is 0. This is 0. And this is 2 times the integral from 0 to pi over 2 cosine x dx minus 5 times 0. And the reason is to recall that cosine x is even and sine x to the power of 5 is odd. Okay. So with this, we're ready to do our integral. The integral of cosine x, the antiderivative of cosine x is sine x. So we just have 2 times sine x pi over 2, 0. If you plug in 0, you get 0. If you plug in pi over 2, you get 1. So our answer is actually 2 times 1, which is just 2. All right. Now, I want to do a few other things in this section of the textbook. They're not quite related to odd and even functions, but I want to do them. Or you know what? I'm just gonna do them in class. How about that? All right, so I will see you in the next one.